Good evening, Kana. So we have been discussing BCC, that is Basic Concepts of Chemistry, right? We are almost done with the chapter. Finally, we have been discussing the concept called solutions, right? And in which we have been discussing the way in which concentrations can be expressed. What are all the concentration terms we have discussed already? Concentration terms like molarity, molality. We have discussed normality also, right? And we discussed also a few numerical related to solutions, right, Kana? Okay, what is molarity or what is the formula to calculate molarity of a solution? Molarity, capital M. Molarity is equal to number of moles of solute divided by volume of the yes, Rakshan. Number of moles of solute divided by volume of the solution in liters, right? Okay. How about molality? What is the formula to calculate molality? Okay, I'll tell you the representation and please tell me the expression for that. N2 divided by W1. For molality, the representation is N2 divided by W1. What is N2 and what is W1?
Number of molecular
Small n is nothing but number of moles. Small n is number of moles. If the subscript is 2, then that is the number of moles of solute. Right, Karna? So number of moles of solute divided by what is W1? W is nothing but weight. Weight of what? If the subscript is 1, then it is for solvent. Right? So weight of the solvent has to be in kilogram. Okay, so we have discussed three parameters. One is molarity, and the formula is number of moles of solute divided by volume of the solution in liters. We saw a couple of problems for this molarity, and molality is number of moles of solute divided by mass of the solvent or weight of the solvent in kilogram. And finally, we saw the expression for normality. What is the formula, Kana? Normality is nothing but number of gram equivalents of solute divided by volume of the solution in liters, right? And what is number of gram equivalents? We know the formula of number of moles, right? What is the formula of number of moles? Given mass divided by molar mass. Similarly, for number of gram equivalents of solute, we saw the expression in the last class. Given mass divided by equivalent mass. Equivalent mass of the solute. And there is a formula to calculate equivalent mass also. What is the formula? Molar mass of the solute divided by n factor. Right, Kana? So I'm going to substitute this equivalent weight in this expression. So see, normality is equal to, instead of number of gram equivalents, I can write it as weight of solute divided by equivalent weight of solute into volume of the solution in liters. And similarly, weight of the solute divided by, instead of equivalent weight, I can write it as molecular weight of the solute divided by n factor. I'm going to bring the denominator's denominator to numerator. I'm just taking the reciprocal of it into volume of the solution in liters. Right, Kana? So this is the expression for normality. Kana, what is this n factor? For acid, n factor is nothing but number of replaceable H plus ions, right? Last class we calculated n factors for few acids, right? For sulfuric acid, for orthophosphoric acid and all, we have calculated n factor, right? For acid, Yes. So for acid, N factor is its basicity. Basicity is nothing but number of replaceable H plus ions. So what is the formula to calculate equivalent weight of the acid? Molecular weight of the acid divided by basicity of the acid. Basicity of the acid is nothing but number of replaceable H plus ions. Similarly, for base, equivalent weight is equal to molecular weight of the solute divided by, for base, the N factor is acidity. Acidity is nothing but number of OH minus ions. For example, my base is sodium hydroxide. And what will be the acidity of sodium hydroxide? Acidity of sodium hydroxide. The sodium hydroxide got only one OH minus ion. So acidity or the N factor of sodium hydroxide is 1. Right, Kana? Similarly, for calcium hydroxide, what is the acidity of calcium hydroxide? Acidity of calcium hydroxide is 2. Senthil was right because this calcium hydroxide got 2 OH minus ions. For aluminium hydroxide, acidity is 3. Right, Kana? So, commonly basicity, acidity can commonly called as N factor. Fine, right? So this is the expression for normality. I'm going to highlight few parameters. W2 by M2 into volume of the solution. This terms can be written as W2 by M2 into volume of the solution can be written as, what is this?
Molasses.
Molarity. That's it. This is the relationship between normality and molarity. So the important formulas are, for molarity, the formula is number of moles of solute divided by volume of the solution in liters, or instead of number of moles, I can expand number of moles as weight by molecular weight into volume of the solution in liters, and unit of molarity is mole per liter. And for molality, the formula is number of moles of solute divided by weight of the solvent in kilogram, or I can expand this number of moles as weight by molecular weight into weight of the solvent in kilogram. And unit of molality is mole per kilogram. Okay. And similarly for normality, the formula is number of gram equivalents of solute divided by volume of the solution in liters. So unit will be number of gram equivalents per liter. Okay. And this can be expanded as weight by molecular weight into volume of the solution in liters and into N factor. That's it. So instead of W2 by M2 into volume of the solution, I can replace it with the term molarity. And this is the relationship between normality and molarity. That's it. So this is molality, and normality. Okay. Now we'll discuss a problem related to these concentration terms. Here's the question. Can anyone read this question? Can anyone read out the question?
How many grams of concentrated nitric acid solution should be used to prepare 250 ml of 2.0 mH?
Three.
The concentrated acid is 70% HNO3.
Thank you, Harini. Actually, the question is related to molarity. See, this is capital M. Capital M represents molarity. So you have to read this out as 250 ml of 2 molar nitric acid. Okay. So here the question is they're asking us to calculate how many grams of nitric acid solution is required to prepare 2 molar nitric acid of 250 ml. Okay, so we have to prepare nitric acid solution whose volume is 250 ml and concentration is 2 molarity. See, here the question is related to molarity, and we know the formula to calculate, or the formula related to molarity, which is weight of the solute divided by molecular weight of the solute into volume of the solution in liters. See, we are provided with the value of molarity, and we can calculate the molecular weight of nitric acid, and the volume of solution is 250 ml. So from these data, we can calculate W2. W2 is nothing but weight of the nitric acid needed. Right, Kana? Here nitric acid is the solute. So W2 is the weight of nitric acid required to prepare 2 molar nitric acid of 250 ml volume. Okay, but unfortunately here nitric acid is not in the powder form. Here in this problem, nitric acid itself is a solution. Now we are in a place to calculate how many grams of nitric acid solution required for this preparation. Okay, so before getting into the calculation of grams of nitric acid solution required, now please calculate what is W2. First, let us understand how many gram of nitric acid is required to prepare this molar nitric acid solution. So first we'll calculate a value of W2, which is the nitric acid, that is weight of nitric acid required to prepare 2 molar nitric acid solution. So left side we have the data, which is 2 molarity. Molarity can be written as mole per liter. I'm going to calculate the value of W2, so I'm just going to cross multiply this. So M2 is nothing but molar mass of nitric acid. Could you please calculate the molar mass of nitric acid? Molar mass of nitric acid. Atomic mass of hydrogen is 1. Atomic mass of nitrogen is 14. For oxygen, it is 16. So let me know the value of M2. Yes, Sendamil Chelvan is right. It is 63 gram per mole. And volume of the solution is 250. It has to be in liters. So the value of milli is 10 power minus 3 liter, which is equal to W2. So here, liter and per liter will get cancelled. Mole and per mole will get cancelled. So could you please tell me the value of W2, Kana? Value of W2. Value of W2. Can I please come up with at least approximate value? Two into 63 into 250 into 10 power minus 3 gram. Yes. So it is 31.5 gram. So we need 31.5 gram of nitric acid to prepare 2 molar nitric acid solution. But in our lab, nitric acid is in solution form. That itself is a solution, and the concentration of that solution is 70%. What the 70% nitric acid solution mean is, if you take 100 gram of this nitric acid solution, in that 100 gram, 70 gram was nitric acid and remaining 30 gram was water. Okay, so if you take 100 gram of nitric acid solution, 70 gram was nitric acid and remaining 30 gram was the weight of water. Okay, now according to this problem and according to this data, we know that 31.5 gram of nitric acid is required. So I have this nitric acid solution, and if you take 100 gram of nitric acid solution, then that contains how much gram of nitric acid? It is 70 gram of nitric acid, right? So how much gram of nitric acid we need? It is just 31.5 gram. So how much quantity of nitric acid solution I should take? That is X. So if you take 100 gram of the solution which contains 70 gram of nitric acid, and we are in need of just 31.5 gram of nitric acid, so for which how much gram of nitric acid solution you'll be weighing? That is X. You just use this unitary method to find the value of X, and that is the answer. Yes, it is 45 gram of nitric acid. Sindhamar Chilvan is right. See, half of 70 is 35. In fact, we need only 31.5. It is less than half, right? So similarly, half of 100 is 50, but we need less than 50. So obviously the answer is option D, right? That's it. Now we'll move on to next problem. 0.63 gram of oxalic acid is dissolved in 250 ml of solution. Calculate the normality of the solution. So here the problem is related to normality, and we know the formula, right? Weight of the solute divided by equivalent weight of the solute into volume of the solution in liters. So what is the equivalent weight of solute? It is molecular weight of the solute divided by n factor, right, Kanna? So here the solute is oxalic acid. Could you please tell me the formula of oxalic acid? Formula of oxalic acid. Oxalic acid's formula is COOH bond COOH with 2 moles of water molecule. So this is the formula of oxalic acid. Here, from this formula, we can calculate the value of M2, right? And since this is acid, the N factor is basicity. So for this acid, basicity is, we have 2 H plus ions which are directly connected to carbonyl group. So basicity is 2. That's it. So please calculate the molecular formula of this complete compound and substitute in place of M2, and the N factor here is 2, and weight of oxalic acid is given as 0.63, and volume of the solution is 250 ml. Convert that into liter and simplify and let me know the value of normality. The only catch is we have to know the formula of oxalic acid, and it has 2 molecules of water. Okay, and you have to know the basicity. I've given all the data. Please substitute the values and let me know the value of N. Okay. Sendamit Children's answer is option 4. Okay. Now if you change to option C, Can I please check your calculation? What is the molecular weight of oxalic acid? What is the molecular weight of oxalic acid? You have to include water's weight also. Yes, it is 126. So, molecular weight is 126. N factor is 2. So, what is the equivalent weight? It is 63, right? So, normality is equal to given mass is 0.63 divided by equivalent weight is 63 and volume of the solution is 250 into 10 power minus 3 liter. So simplify this. 0.63 can be written as 63 into 10 power minus 2 divided by 63 into 250. I can bring this numerator, I can bring this 10 power minus 3 to numerator, which is 10 power plus 3. That's it. So 63 will get cancelled out. Now simplify this and let me know the value. So normality is equal to 10 divided by 250 or 1 divided by 25. So what is the answer, Kanna?
D, ma'am.
Kanna, is it option 2 or option 4?
2, ma'am.
Option 2. That's it. Okay. So the next problem. Calculate the molarity and normality of a solution containing 0.5 gram of sodium hydroxide dissolved in 500 ml of solution. So for the same solution, they're asking us to calculate molarity and normality as well. We need not calculate individually. We know the relationship between molarity and normality. The relationship is normality is equal to molarity into N factor. What is the N factor of sodium hydroxide? What is the N factor of sodium hydroxide? N factor of sodium hydroxide. Sodium hydroxide is a base. So for base, the N factor is acidity, that is number of OH minus ions. So sodium hydroxide contains only one OH minus ion. So the N factor is 1. So for sodium hydroxide, normality is equal to molarity. So obviously we can screen the options, right? Normality and molarity has to be equal. So option A is ruled out and option D is also ruled out, right? So among B and C, we have to find the right answer. You just calculate the molarity and let me know the value. Molarity. So the answer is second option. So molarity of the solution is 0.025. Okay. Since N factor is equal to 1, for this kind of solution, normality is equal to molarity. So normality is also 0.025. Right. So till now we have discussed three consideration parameters. One is molality, another one is normality. Now we'll discuss one more parameter which is called mole fraction. Mole fraction can be represented with an alphabet capital X. See, for example, in a solution, I have three components A, B, C. Quantity of A, that is number of moles of A is Na. Number of moles of B is Nb. Number of moles of C is Nc. And all these three components forms a homogeneous mixture, which is a solution. As far as mole fraction is concerned, we can write the mole fraction of all the components inside the solution. So here in this case I have three components A, B, C. For all the three components I can write the mole fraction. What is the general representation of concentration? It will be in fraction. In numerator it will be quantity of the solute, and in denominator quantity of the solvent or solution. Similarly, I am going to write the mole fraction of component A. So I am going to write the quantity of the A in the numerator. So quantity here is number of moles. So number of moles of A divided by, in denominator I'm going to add all the number of moles. I mean all the components number of moles, which is Na plus Nb plus Nc. That's it. Similarly, what is the mole fraction of B? If mole fraction of A is number of moles of A divided by Na plus Nb plus Nc, then what is the mole fraction of B? What will be in the numerator?
Number of moles of B by number of moles of A plus number of moles of B plus number of moles of C.
Very good. Similarly, I can write it for mole fraction of C. That is number of moles of C divided by number of moles of A plus number of moles of B plus number of moles of C. So as far as mole fraction is concerned, we can write the mole fraction for all the components in the solution. And also you have to know that if you add all the mole fractions, then it will be always equal to what? If you add all these mole fractions, it will be equal to what? You add and see. See, what is XA? Number of moles of A divided by total moles. What is XB? Number of moles of B divided by total number of moles. And what is XC? Number of moles of C divided by total number of moles. So the common denominator is Na plus Nb plus Nc. So if you add all the numerators, it is also Na plus Nb plus Nc. So if you cancel this, it is equal to 1. So if you add all the mole fractions, then it will be always equal to 1. Okay, that's it. Fine, Kana. So this is also a way of expressing concentration. Okay, and we have to know one more thing in concentration discussion. And I listen here. There are two way of preparing solution. One is I'll be having some solute, and then I'll be having a particular quantity of solvent. For example, sodium chloride and water. I have sodium chloride powder or sodium chloride salt, and I'll be having water. I'm going to take few grams of sodium chloride and I'm going to dissolve it in water. So I'm going to prepare a particular concentration of sodium chloride solution. This is one way of preparing solution, and this is how we have discussed the problems also. But there is another way of preparing solution. See, initially itself I'll be having some highly concentrated solution. Okay, I'll be having some stock solution whose concentration will be very high. What I'm going to do is, see, maybe the concentration of this solution is M1. So this is the molarity of the stock solution. I'm going to take few ml of this solution in a fresh beaker, and I'm going to add a particular quantity of water. Basically what I'm doing, I'm adding water to dilute the solution. What is dilution? Basically by adding water, you're decreasing the concentration, right? See, what is the formula of concentration? Concentration is equal to number of moles of the solute divided by volume of the solution. By adding water, you're increasing the volume. If volume is increasing, then concentration of the solution will get decreased. And this process is called dilution. So from the concentrated solution, I'm going to take few ml and I'm going to dilute it to a new solution whose concentration will be different from the initial concentration. Okay, this is another way of preparing the solution. So what first way is you'll be taking a proper solute and you'll be mixing it in solvent. Another way of preparing solution is you'll be having some concentrated solution from where you'll be taking a particular ml and you'll be diluting it to prepare another solution of different concentration. Okay, so this is called dilution, and they may ask you questions from this dilution also. They may ask you what will be the concentration of this resultant solution. Okay, so there is a famous formula which is called dilution formula for this. This you have studied in your 10th standard also in your lab. The formula is V1 M1 which is equal to V2 M2. This is about the stock solution or the concentrated solution, and this is about your resultant solution, new solution. So V1 is the, please note it down, Kana. V1 is the volume of the stock solution taken. V1 is the volume of the stock solution taken. Stock solution taken, or highly concentrated solution. Volume of the concentrated solution taken. And M1 is the concentration of the solution, concentration of the stock solution. If the concentration in molarity, then it is M1. If the concentration was expressed in normality, then that will be N1. Okay, it depends. Here I've written M1. If it is in the problem, it is normality, then have it as N1. So M1 is the concentration of the stock solution. And similarly, V2 is the volume of the resultant solution. Resultant solution is nothing but the final new solution. Okay. And M2 is the concentration of the resultant solution. Since you are adding water, you are basically diluting the solution so that the concentration of new solution will be lesser than the initial solution. Okay, fine. Shall we move on to a numerical related to this dilution? Shall we?
Yes, ma'am.
Fine. Here is the problem. Kana, if 25 ml of 0.25 molar sodium chloride solution is diluted with water to a volume of 500 ml, the concentration of the new solution is dash. So here the problem is related to dilution, and they're asking us to calculate the concentration of new solution. You have all the data, Kana. Please calculate and let me know. So Sendamil children's answer is option A. Okay. So how to do this? The formula is V1 M1 which is equal to V2 M2. So 25 ml of 0.25 molar sodium chloride. This is the stock solution. This is M1 and this is V1 and this is the V2. This is the value of V2. So basically we need to calculate M2 just by substituting and rearranging. We can find the value of M2, right? That's it. So we are done with this chapter. So we are done with this basic concepts of chemistry. See, now we have discussed the concepts and we have discussed the numerical related to those concepts. Okay. And now your job is to practice. Now you know the concept and you know how to apply the concept also. Now you have to practice, Kana. You have to take any publications and please practice. Okay, at least you have to solve 50, 60 questions from this chapter to get familiar with the concepts. Okay, there is no use in keep on reading the concepts. You have to solve numericals. Fine. Okay. So now shall we move on to next chapter? See, as far as basic concepts of chemistry is concerned, you have to solve numerical. Definitely, you have to solve numerical related to limiting reagent, concentration part, and also finding empirical and molecular formula. And unit conversion is a very basic thing. Definitely, you have to know. Okay, but please concentrate on this limiting reagent part and concentration part, empirical molecular formula, and all that. Okay. Now we'll move on to next chapter of 11th standard, which is atomic structure or quantum mechanical model of an atom. Shall we? Shall we start second chapter, Kanna?
Yes, ma'am.
Fine. So the chapter is atomic structure. See, the purpose of this chapter is to discuss the structure of atom. We know everything in this universe is matter, and all the matters are made up of atoms, right? So atoms are the basic fundamental unit of all the matters in this universe. But atoms are very tiny and it is not visible to our naked eye. But without atom, none of the things are exist in this universe, right? So atoms are very very important, but we don't know the structure, or we don't know, I mean, we couldn't see the atoms in our naked eye. But at various time periods, by various scientists, a few structures were given to this atom. Okay, but it may not be 100% true, right? Because we didn't see the structure, because using various theories and using various experiments, different scientists were proposed their structures based on their experimental result. Everything need not be 100% true. So after a few years, another scientist came, and they'll be another scientist will be coming, and they'll be contradicting the points given by the previous scientist, and they'll give you the different model for the atom, right? That is how this chapter goes initially. So there are very important scientists like John Dalton, J.J. Thomson, Rutherford, very importantly Bohr. uh, these scientists were given their point of view about the structure of the atom, right? And I want you guys to read the atomic model of Rutherford, J.J. Thomson, John Dalton. Okay, these were relatively theory, and I want you guys to read from your end. Is it possible for you guys to read, Kanna? John Dalton's atomic model, J.J. Thomson's model, and Rutherford's model. See, J.J. Thomson's model is nothing but your watermelon model, right? He compared the structure of atom with watermelon. And Rutherford's model, what are the things you have remembered about this Rutherford's atomic model? He done an experiment, right? What is the name of that experiment, Kanna? He used some foil and all.
Alpha scattering, ma'am.
Very good. Alpha scattering experiment, and he used gold foil. Okay, right. So I want you guys to read the atomic structure proposed by John Dalton, J.J. Thomson, and Rutherford. Okay, fine. In our class, we'll start with Bohr's atomic model. Okay, fine. Kana, what are all the points you remember about this Bohr's atomic model? we can expect problems from this model. Okay, fine.
This is positive charge nucleus and
Hmm.
electrons orbiting it.
Yes, actually, according to Bohr, first of all, he tried to explain the structure of hydrogen atom, not any other atom. It is just the hydrogen atom structure. Okay. Why? Because this is the simplest atom we have. What is the symbol of hydrogen? What is the symbol of hydrogen? It is H. And what is the atomic number?
One.
1. And what is the mass number? It is also 1. Right? Actually, whenever you're writing or you're representing any atom, you have to know the symbol of the atom, and also you have to know the atomic number and mass number. Z is nothing but atomic number. And A is nothing but mass number. What this atomic number represents? All the atoms will have atomic number, Kanna. From that atomic number, what we can understand is number of protons in the atom. See, all the atoms will have subatomic particles. Subatomic particles are nothing but particles which are present inside the atom. Basically, atom contains three subatomic particles, namely proton, neutron, and electron. Right? So here atomic number represents number of protons in an atom. Okay. And what is the charge of proton? What is the charge of proton? What is the charge of proton? It is positive. Okay. See, we have three subatomic particles: proton, neutron, and electron. This is positive. Electron's charge is negative, and there is no charge for neutron. Yes, protons are positively charged. Could you please tell me the charge, the quantity of charge? It is positive, Karna, but what is the quantity? What is the charge of electron? It is negative, but there is some quantity for that charge. It is easy. 1.6 into 10 power minus 19. What is the unit of charge? Unit of charge is Coulomb, capital C. So the charge of electron is minus 1.6 into 10 power minus 19, and for proton it is again plus 1.6 into 10 power minus 19. Okay, and there is no charge for neutron. And similarly, mass. What is the mass of proton, neutron, and electron? Mass of electron is very famous, right? You'd have used in many numerical. Mass of electron is 9.1 into 10 power minus 31 kilogram. And mass of proton is 1.6 into 10 power minus 27 kilogram. And mass of neutron is also 1.6 into 10 power minus 27 kilogram. Okay. Could you please tell me which is the lightest subatomic particle? Which is the lightest subatomic particle? Electron, because the value is very small. It is 9.1 into 10 power minus 31 kilogram. It is very small, right? So It is the lightest subatomic particle. Similarly, you have to know which is the heaviest subatomic particle. From the value of masses in kilogram, we cannot find whether it is proton or neutron, right? From the value given here, we cannot predict which is the heaviest, but I'll give you the mass in AMU. Sendam Children's answer is right. He's telling me the heaviest one is neutron. He's right. And I'll tell you the value, okay? See, here I've written in kilogram, right? But I can express this mass in terms of atomic mass unit. From the value of atomic mass unit AMU, you can find which is the heaviest also. Protons values 1.0073 AMU. Approximately, we'll be using it as 1 AMU, but this is the exact value. And for neutron, it is 1.0087 AMU. This is also approximately 1 AMU, but from the approximate value, we cannot predict which is the heaviest one. So that is why I've written the exact value. And the mass of electron in terms of AMU is 0.0005 AMU, and approximately we'll be having it as 0 AMU. Okay, so we know the lightest one is electron and the heaviest one is neutron. Okay, fine. So these are all this basic data we have to know about this subatomic particles. We cannot expect these data in our numerical also. So you have to memorize these values. Fine. Now we'll come to this atomic number, mass number part. So atomic number always represents the proton count. And always in an atom, actually atoms are basically neutral. What is mean by neutral, Kana? What is mean by neutral? If the system is said to be neutral, then that contains no charge, or that system contains equal number of positive and negative charges, right? So here atom contains equal number of positive charge and negative charge, which means number of protons or number of electrons are equal. Okay, that is why atoms are neutral. So from atomic number, we know the value of proton count, and we know atoms are neutral. So proton count will be equal to electron count also. So from the atomic number, we can predict the number of electrons. Okay, but atomic number is nothing but the proton count. From the value of proton, we are guessing the number of electrons. That's it. Fine. And mass number represents the sum of number of protons and number of neutrons. Okay, so from the atomic number, we can predict the number of protons and number of electrons. And from the mass number, we know the sum of proton and neutron. Okay, so now you have to know the number of neutrons. Is there any way to calculate number of neutrons, Kana? Because from atomic number itself, we can predict number of protons and number of electrons. What is the way of calculating number of neutrons? See, atomic number mass number represents number of protons and number of neutrons. So if you know this value, from this value, if you subtract this number of protons from mass number, if you subtract number of protons, you'll get the value of neutron count, right? What is this number of protons? Nothing but your atomic number. So mass number minus atomic number will give you number of neutrons. Okay, that's it. So this is the symbol, and bottom we'll be having atomic number and top we'll be having mass number. So according to hydrogen, what is the proton count? Atomic number is 1. The proton count, it is 1. And what is the electron count?
1.
It is also 1. And what is the count of neutron? Mass number is 1. Atomic number is also 1, so it is 0. So hydrogen doesn't have neutron. Okay, so hydrogen is the very simple atom, because according to Bohr, see, hydrogen got nucleus, and inside nucleus we'll be having proton and neutron. As far as hydrogen is concerned, we have no neutron, but inside nucleus we'll be having proton, right? And electrons will be revolving around the nucleus in a particular path. So what this path is called? What is the name of this path? It is called orbit. What is another name for orbit? What is the other names for orbit? It is also called as shell, or it is also called as energy level. Okay, so according to Bohr, um, atom contains nucleus at the center, and nucleus contains protons and neutrons. And since protons are positively charged, the charge of the nucleus is positive, and the negatively charged electrons are revolving around the nucleus in a particular path, which is orbit. Okay, you guys are clear with this concept, Kana? Are you guys clear? Are you guys
Yes,
getting the
ma'am.
point? Fine. Right. Now we'll move on to few formulas related to this Bohr's model. See, according to Bohr, he used only hydrogen atom because hydrogen is the very simple atom because it contains only one electron. And if you place the if you place the electron in a proper position or proper place, then whole structure was defined, right? So he used hydrogen atom, and in that one electron is, according to Bohr, it is revolving around the nucleus, right? So the electron which is revolving around the nucleus will have some amount of energy, right? So there is a formula to calculate the energy of the electron which is revolving around the nucleus. According to Bohr, around this nucleus we have n number of energy levels. Okay, not only one. All the atoms contains n number of energy levels, but electrons are present in particular energy levels. According to hydrogen, hydrogen got only one electron and it is present in only one shell, and rest of the shells were empty. But generally, atoms has infinite number of energy levels. Okay, but in particular number of energy levels, electrons will be there. As far as hydrogen is concerned, hydrogen got only one electron and it is present in one of the shells, right? If the electron is present in first shell, then that electron will have particular amount of energy. If the electron is present in second shell, then it will have different energy. If the electron is present in sixth shell or fifth shell, and it will have a particular amount of energy, and that energy of the electron can be calculated using the formula minus 13.6 Z square divided by n square. Here En, and the unit of energy is electron volt. Okay, fine. Here n is the energy level in which electron is present. And could you please tell me what is this Z represents? What this Z represents, Kanna?
Proton. Number of protons.
Number of protons or atomic number? Since Bohr is talking about only hydrogen, atomic number of hydrogen is 1. Okay, but these concepts can be applied not only to hydrogen, but we can also apply to a single electron system. See, hydrogen is a single electron system, and similarly we can apply his concept to single electron systems. For example, helium. Kana, is it a single electron system? How many electrons does helium atom got? How many electrons does helium atom got?
2 electrons.
Very good, Rakshan. So we cannot apply Bohr's concept to helium atom. But if you remove one electron from helium, it will become helium plus. Now it is a single electron system. Initially, helium got 2 electrons, in which I've removed 1 electron. Now helium was converted into helium plus, and I can use Bohr's model to helium plus. But atomic number of helium is, what is the atomic number of helium, Kana? It is 2 and not 1, because atomic number represents proton count and not the electron count. Though I have removed 1 electron, Still proton count is 2, so atomic number is 2. So whenever you're writing the formula, please represent this atomic number, don't leave this one. Okay, if it is hydrogen, then atomic number is 1, it will become minus 13.6 divided by n square. But whenever you're applying the Bohr's model to any other single electron system, atomic number will be, it will not be 1, right? So you should not leave that z in the formula. Please mention atomic number in your formula, right? Similarly, we cannot apply Bohr's model to lithium, but we can apply to lithium 2 plus. What is the atomic number of lithium?
3, ma'am.
3. Right. Now we'll talk about hydrogen. For example, now only one electron in hydrogen is present in first shell. Okay, now we'll calculate the energy of the electron which is present in first shell. So E1 is equal to minus 13.6. Since the atomic number of hydrogen is 1, it is 1 square. Now the electron is present in first shell, so it is also 1 square. So value is minus 13.6 electron volt. Right. Now what this minus represents? Energy of the electron is minus 13.6 electron volt. What this minus represents? Why it has to be in negative sign?
It gives out of energy.
Very good, Kana. Very good. Whenever the system is losing its energy, the quantity will be represented with negative sign. Whenever we are supplying the energy to the system, it will be positive, right? Now here, whenever the electron is present in the atom, there is a force of attraction between nucleus and the electron. Whenever there is an attraction, a particular amount of energy was released. Here 13.6 electron volt of energy was released. That is why it is minus. Okay, fine. If the electron is present in second shell, then the energy of the electron is minus 13.6. Though the electron is present in second shell, atomic number is same, right? It is 1 divided by 2 square. So could you please calculate and let me know the value of E2? What is the value of E2? Minus 13.6 divided by 4.
3.41.
Yes, it is minus 3.4 electron volt. If it is E3, minus 13.6, 1 square divided by 3 square. What is the value, Kanna?
Minus 1.51.
Okay, is it minus 1.51? 13.6 divided by 9. So, minus 1.51. Okay. Kana, now tell me, as the value of n increases, what is happening to the energy? Is it getting increased or decreased? From minus 13.6, it is getting converted into minus 3.4. And it is getting converted into minus 1.51. So the energy is getting increased, right? The negative values keep on decreasing. So if n value increases, if the electron is moving away from the nucleus, the energy of the electron is getting increased. Okay, Kana, listen. If the electron is moving away from the nucleus, the energy of the electron will get increased. And we know energy and stability are inversely proportional. Now tell me, in which state electron will be very much stable? in which state electron will be very much stable. For more stability, how should be its energy? For more stability, energy has to be
lesser.
lesser. Very good. So among these values, which got less energy? It is minus 3.6, right? So as far as hydrogen is concerned, if the electron is present in first shell, this got lowest energy, and this is the very stable state for this electron, and this is called ground state. And rest of the states are called, if that is ground state, rest of the states are called, you know the term, excited states. So the excited state which is closer to the ground state is first excited state, and this is second excited state, and goes on. Okay, fine. You're getting my point? Okay. Now I have another question. Kana, listen. I have hydrogen atom, and in hydrogen atom I have only one electron which is present in first shell. Okay. Now I want to remove this electron. Now the electron is present in first shell, and I have to remove this electron. So for that I have to break this attractive force between nucleus and the electron, right? So to break the attractive force, I have to supply a particular amount of energy on this electron, right? So how much amount of energy I have to supply on the electron to remove this from the atom? It is same the energy, it is the same as the energy of the electron. See, if the electron is present in first shell, the energy of the electron is 13.6. So I have to apply same amount of energy on the electron to remove it from the first shell. So the energy supplied on the electron to remove is called ionization energy. See, the amount of energy supplied on the electron to remove it from the ground state, then that energy supplied is called ionization energy. Since the amount of energy I'm supplying on it, it is represented with positive sign. You're getting my point? If the electron is present in ground state, then the amount of energy supplied to remove that electron is called ionization energy. If the electron is present in any of the excited states, then I can supply a particular amount of energy to remove that electron, but the energy supplied is called separation energy. See, ionization energy is the amount of energy required to remove the electron from ground state, and separation energy is the amount of energy required to remove the electron from any of the excited states. Okay, fine. What is the separation energy if the electron is present in second state? What is the separation energy if the electron is present in second state? What is the separation energy if the electron is present in second state, Kanna? It is already there. What is the energy of the electron if it is present in second energy level? It is minus 3.4, right? So same amount of energy I have to supply on the electron. So it is plus 3.4. So plus 3.4 is the separation energy if the electron is present in second energy level. You getting my point? Are you guys clear? Fine. Kana, this is the only formula you can memorize. But sometimes in a problem, they may ask you the value of energy in terms of joules and calories and all. But you just memorize this formula alone, and always there is a conversion for this energies, right? For example, 1 electron volt is equal to 1.6 into 10 power minus 19 joule. So calculate the value in electron volt, and if they are asking it in joule, please use this conversion. Okay. And similarly, 1 calorie is equal to 4.18 joule. And also 1 joule is equal to 10 power 7 ergs. So you can use either electron volt or joule or calorie or ergs to express the value of energy. Okay, so memorize only this formula. If you calculate it in electron volt, you can always convert to rest of the units. Okay, and this is the formula to calculate the energy of the electron according to Bohr. Now we'll move on to radius. As we know, atoms are spherical. The parameter radius is applicable, right? So we have to know what is atomic radius. We know at the center of the nucleus we have at the center of the atom we have nucleus, and around nucleus we have energy levels in which electron is present, right? This is nucleus. Okay. If the electron is present in first energy level, then the distance between center of the nucleus to the shell in which electron is present is the radius. If the electron is present in second shell, then the distance between the nucleus and the second shell will be the atomic radius. Okay. Now tell me, Kanna, if the value of n increases, what is happening to radius? Is it getting increased or decreased? If n value increases, what is happening to the radius? If n value increases, what is happening to the radius? Is it getting increased or decreased?
Increase.
Increase. So it is, they are directly proportional, right? So the formula to calculate radius is Rn, which is equal to 0.529 n square divided by z, and the unit is angstrom. Angstrom is nothing but 10 power minus 10 meter. That's it. For example, if I am talking about hydrogen, and the one electron which is present in hydrogen is in first shell. Could you please calculate the radius? In hydrogen, electron is present in first shell. So what is the radius, Kana? R1 is equal to 0.529. Value of n is 1. So it is 1 square divided by atomic number of hydrogen is 1 angstrom. So R1 is equal to 0.529 angstrom. Unit is important. Okay. Okay. For example, I have lithium 2 plus. Okay, in lithium 2 plus, how many electrons will be there?
1.
So it is a single electron system. Definitely, we can use Bohr's concept to this lithium ion. And this electron is present in third excited state. Now I want you guys to calculate the radius. Electron is present in third excited state, and I want you guys to calculate the radius. Since it is lithium, you know the value of Z, right? But you have to know the value of N, and they didn't give the value of N directly. They are talking about excited state. If it is third excited state, then what will be the value of N? Calculate accordingly and come up with the value of radius. What is the value of n? See, if n is equal to 1, then that is ground state. If n is equal to 2, then that is first excited state. If n is equal to 3, then that is second excited state. If n is equal to 4, then that is third excited state. So what is the value of n? It is 4. So 0.529 n value, so it is 4 square divided by atomic number of lithium is 3. That's it. Let me know the value of R. What is mean by excited state? Okay, Ashmit. Kana, if see, excited state is nothing but, as far as hydrogen is concerned, if the electron is present in first state, this is the energy level in which electron got very lowest energy, right? So that is the ground state. But in rest of the energy levels, energy is getting increased, right? So the energy level or the shell in which electrons energy is lowest, that is called ground state, and rest of the energy levels are called excited states. The energy level which is closer to the ground state is called first excited state, next is second excited state, next is third excited state, and goes on.